here's a polymerization reactor. At giant scale, you can see this is being pulled by a truck. You've got inlets and outlets and ports for sensors and monitors. Put hot and cold, maybe if it's an exothermic reactor, you put some cooled water there and pull heat off as it goes, or if you need to heat it up, do the opposite. This is the other extent of scale. This is a reactor on a chip. A microchip where we etch in or have a pattern or a mold that we can make tiny channels. You can push stuff in through these with syringes, through inputs, mix stuff, and then as it goes through, this is, we talked about plug flow and mixed reactors. This is a plug flow reactor. It takes a bit of time to go through all of this. But you can also make polymers up here, just like the giant reactor on the slide before. There's an industrial scale polymerization. Here's a chip scale polymerization, and then there's a port here where you can pull out your product at the end. And then here's a pharmaceutical batch reactor. So a batch reactor, you put stuff in and then pull stuff out. There's usually a mixer inside here, a vent for gases to come off, ports for reactants to go in. And again, there's usually a jacket of some sort for coolant or for heating on the outside. So we were talking a couple of days ago about combustion of natural gas. We talked about the Marcellus Shale, pulling gas out of the ground a mile below. And then we did a whole bunch of compound balances, mole balances with Vibe reactions to solve the flows. And then at the end, we mentioned briefly that you could do this whole thing with atom balances. So I'm going to go through that solution. We do atom balances in the reactor furnace where we're going to burn this natural gas. We're going to feed in the natural gas. We're going to feed in air. And we're going to pull out exhaust. We'll write out the atoms. We've got carbon, hydrogen, oxygen, and nitrogen going in from the natural gas. We don't need to worry about whether it's methane or ethane. We're just going to lump all of the carbon together, lump all the hydrogen together, etc. And in the air, we're going to have oxygen and nitrogen, and maybe we'll ignore that it's O2, which is where the moles of oxygen atoms. And then in the exhaust, we're going to have the same kind of atoms coming out. C, H, O, and N will have to come out. It'll just be different compounds. And then if it's combustion, okay, so what we'll do in atom balance is we'll take our compounds, we'll shift it into atoms, push it through the other side, and then we'll put it back into compounds again. So after we do that, we'll put this back into CO2, H2O, nitrogen, and there was extra oxygen, right? Okay, so what's our atom balance on, what's our material balance on atoms? So atoms, we're dealing with, let's see, accumulation is in minus out, plus gen minus consumption. We've got atoms, so we can't generate or consume those unless we're doing nuclear reactions, and we're not. So I'm going to write, this would be sum of the flow rates, Nij, for the inlets, minus, there's one outlet, so Ni out equals 0, or Ni 1 plus Ni2 equals Ni out. The other balance for each component. So carbon in the gas plus carbon in the air equals carbon in the exhaust. And the strategy, so we can take compounds, change them into atoms. When we do our material balances, we'll have our atoms coming out, or things we didn't know, and then we'll switch back to compounds. So the atoms coming in, if we do carbon coming in, we're going to have to add up 1 mole of carbon for each CH4, 2 moles of carbon for each ethane, 3 moles of carbon for each propane, etc. So we're going to add those together. We're going to do the same thing for the hydrogens. So let's see, stream 1, the number of moles of carbon going in is going to be a sum of the number of moles of each compound I, the number of moles of CH4, times epsilon HI, or epsilon carbon I. If you remember, our epsilon is the number of atoms in each compound. So then this would be over the compounds I. So this would be 1 times n dot CH4 plus 2 times n dot C2H6 stream 1 plus 3 times n dot C3H8 stream 1, etc. And I do the same thing for the hydrogens and the oxygens and stream 2 and stream 3. Should write me an equation for, say, this side of the room do the oxygens, that side of the room do the nitrogens, and everybody do the hydrogens. Go ahead.
So there's 4 n dot CH4.
4 times n dot CH4
plus 6 times n dot C2H6
plus
8 n dot C3H8
plus
10 times
10 n dot C4 plus 12 n dot C5. And then I've got the compositions of the gas and the air. N dot in the gas and the air of each of these components, and then I split it into 4 atoms, C, H, O, and N. Here's epsilon H of I, that's our multiplier. So there's 1 carbon in CH4, 2 in CA2H6, 3, 4, 5. There's 4 hydrogens in CH4, 6, 8, 10, 12. CO2, there's 1 carbon, 2 oxygens, nitrogen and oxygen. And then I do the math here to multiply those out. So the amount of carbon is, in the first stream, is the epsilon 1 times the flow rate of methane. Same thing down the line for each of these, and then we total them up. So this is carbon in the methane, ethane, propane, etc., and then this is total carbon at the bottom. Just sums up what's above it. Does that make sense? Do the same thing for hydrogens and oxygens and nitrogens, and I don't have to type out all these formulas because I use the $sign for column F here and not the $sign for this column, and so as I copy this across, they all come out. I get the totals for each of the atoms, carbon, hydrogen, oxygen, nitrogen. Then what goes in has to come out. So the in for carbon has to be the out for carbon. The in for hydrogen, oxygen, and nitrogen. And then there's a little bit of a game to match this up. So all of the carbon comes out as CO2. So I take that 70.3. Okay, let's see. So this 70.3 just points the out, matches the in. And then the CO2 just matches the carbon in. The nitrogen, carbon in or out, it's the same thing. The nitrogen matches the nitrogen in. The hydrogen matches the hydrogen in. And then the oxygen you've got to kind of resort out. So you know the H2O because you've got to have 2 oxygens for every hydrogen. Do the flow rate of water, you can take the hydrogen flow rate divided by epsilon. So I've got 2 hydrogens in every water, so half of that will give you the flow rate of water. And from that flow rate, I can go back and get the flow rate of oxygen in the water. And then same thing for these two. From N2, I can take half of that and the flow rate from the nitrogen atoms, and half of that is the nitrogen gas. From the carbon atoms, that should be equal to the carbon dioxide, because there's 1. So for the O2, I've got to take the total oxygen, subtract what comes out in H2O, subtract what comes out in CO2, and then I get the O2. That gives me the flow rates of each of these components. And that should match what we had, and then I can get the composition, and that should match what we had when we did the compound balances. All right, so I know it's hard to follow a little bit out in PowerPoint, or on Excel. Any questions about where the formulas come from? How to approach it?
This question doesn't have anything to do with the process, but how hard would it be to separate out the water from everything else?
How hard is it to separate water from nitrogen, oxygen, and carbon dioxide? That's a great question. Chapter 5 is separations. We'll talk about all this. What properties are different in water compared to CO2, nitrogen, and oxygen?
It's polar.
It's polar. It's liquid. It's H2O liquid.
At room temperature.
At room temperature. Any others? At room temperature?
No.
Everything else is a gas. So yeah, if you just cool it off to room temperature, you get that water out. If these are your flow rates, if you believe your model, it's just pure water. Yeah. Another thing we'll talk about next chapter, chapter 5, we'll talk about, let's say you condense this gas stream, how much CO2 is going to end up in the water, how much oxygen will end up in the water, how much nitrogen will end up in the water. Depends on some physical properties. You can get oxygen dissolved in water, right? Fish have to breathe. So how much is in there? Will that oxygen be safe for you to drink? Yeah, I think so. I don't know. It could be a little bit of methane dissolved in there if that didn't burn. Yeah, good question, Alexander.
So basically, like, the reason why we can figure out the flow rates of the compounds out is because like the number of hydrogen atoms in is half the flow rate of water out, right? But I'm wondering, what if we had like another problem and the output rate was just like a whole bunch of methane, ethane, butane, propane? What if the output was just compounds of C and H, then would we not be able to like?
Yeah. Let's say I add a little methanol in there just to mix up some oxygen. You're right. Now it's not. Now I've got another degree of freedom. It's not necessarily out. If I have another degree of freedom, what does that mean? I need another specification, so you might need to be told you get a trace 0.1% of methanol coming out. Or another one that would make it complicated would be CO. I've got CO. That's going to change things. So now you're going to need to know something about, maybe they'll have to tell you how much oxygen. So you might need to go to the lab and take a measurement, how much CO is in the stream. Yeah. Complete combustion means all carbon goes to CO2, all hydrogen goes to H2O, all sulfur goes to SO2. So if the problem tells you take this compound and we have complete combustion, you know only CO2 and H2O come out. If CO2 only, if it's complete combustion, that means you have no carbon monoxide. If you don't have complete combustion, you're going to have carbon monoxide. All right, so combustion's special like that. For everything else, we have some other language. I think you've heard of this in chemistry class. Excess limiting reactants. Heard these phrases before? Yes. What's an excess? Which is the excess reactant in this process? Is methane limiting?
Yes.
Yes, nothing's coming out. Ethane, which is the excess? What do we react and still get some out of? So the oxygen is our excess reactant. We've got lots of oxygen. We burn all the hydrocarbon and we still have oxygen come out. The oxygen is excess. Okay, let's go to a generic example. Let's say we have A plus 3B goes to D. So how much B do I have to put in to make B the excess reactant? 3 times, right? Okay, so if NA in dot is less than NB in dot, then if A in dot is less than 3 NB in dot, then A is limiting, B is excess, and if NA in dot is greater than 3 NB in dot, then B is limiting and A is excess. Yes? I agree with what we all know. And if A exactly equals 3, then we say, what do we call it if we have exactly 3 and 1 for that sample reaction? Everybody.
Complete reaction.
How about fed in a stoichiometric ratio? Yeah? Okay, so stoichiometric feed rates. All right. Let's see. So in general, A is limiting if N dot A in, we take that inequality and divide NB in on the bottom. NA in over NB dot in equals, no, is less than. Over there, if I divided it out, I'd have is less than 3. Well, 3 is the stoichiometric coefficient for B, and 1 is the stoichiometric coefficient for A. So it's less than nu B over nu A. If I feed 1 mole of A, I should feed how many moles of B? 3. So A's got to be less than 1/3. 3 moles of B times 1/3. If that's greater than 1 mole, then A is limiting. Yeah? This is right. No, that's not right. Nu A over nu B. Okay. And let's see. A is the excess reactant. If N dot A in over N dot B in is greater than nu A over nu B. Okay? All right, I'm doing A and B. We can do this for multiple reactants as long as we use the limiting reactant as the small one. Yeah.
For combustion, if it's incomplete, do we have to have 2 separate equations for carbon dioxide and carbon monoxide, or can we combine them into one?
Let's see. If combustion is incomplete, that usually means which is your limiting reactant. Then oxygen might be limiting. There's not enough oxygen. Right? Okay, so with multiple reactions, this is a little tricky. With one reaction, we can do this. So what we do is we take the complete combustion reaction to CO2, and then we use that reaction to say how much excess or what's limiting. And then if that's not able to go, if we don't have enough, then we're going to get CO, and it's a different thing. So we use the reaction we actually want, the CO2, usually to define this. So for extra excess, percent excess equals NA dot in minus nu A over nu B N dot B in. So if I had exactly the right amount of B, then the amount of A I need would be NB in divided by that stoichiometric coefficient times the stoichiometric coefficient of A. That should tell me exactly how much I should have. So if it's stoichiometric, this quantity should be 0. I'm going to normalize this by how much I should have if it's stoichiometric, nu A over nu B times NB in dot. Now I have a fraction. So how much A I should have. So this is percent excess of A. Let's say that B is the limiting reactant. So B is the limiting reactant. The amount of A I should have is by taking the B in, multiplying by the stoichiometric coefficients. I subtract that from how much I actually have, divide that by the stoichiometric amount. For percent, I need to multiply by 100. Marcellus. Shale gas. We've got 70.3 kilograms per hour of carbon, 243.6 kilograms per hour of hydrogen, and N.O2 in is 254 kilograms per hour. Find percent excess O2. Can we do that in about a minute? So you want carbon to go to CO2. You want hydrogen to go to H2O. Pulling these numbers out of the atom balance, right? This is 70.3 kilogram moles of carbon atoms. Okay, so if I got 70.3 kilograms per hour of carbon, how many kilograms per hour of oxygen do I need to make CO2? 140.6 kilograms per hour. How'd I get that? I would take N dot carbon in times 2 over 1, that would be mu of O2. So this is, I guess the reaction we're doing is C plus O2 goes to CO2. And then, this C plus 2 oxygens goes to CO2. Okay, so I need twice as much oxygen as I had carbon for H2O.
Do you want it to be in kilograms or kilogram moles?
Kilogram moles. Yeah. There's kilograms, I gotta use all those molecular masses. I don't have time for that on the board, but you're likely to find that out on the homework. So. Okay, so hydrogen, 243 kilogram hours. How much do I need? Double that? Half that. 122 kilogram moles per hour, something like that. I'll add that together. I need 263 kg moles per hour. And how much oxygen actually came in? 254 kg moles per hour. So let's need this of oxygen. This is O2. So I need to compare either O2s or compare oxygens. So let's compare O2s because that's what we actually feed. So if that's 263 of oxygen, I need 132 kg moles per hour of O2. So half as much for bimolecular oxygen. Then I want to compare these two. So percent excess is going to be the 254 minus 132 over the 132. So times 100, I get 94% excess in this case. So 94% excess, almost a whole excess, so I should be getting out about half of the oxygen I put in. My spreadsheet wasn't goofed up here. 123 moles came out, 154 moles went in, so that sounds about right. So you should be able to do some checks on this too and see if what comes out matches your percent excess. Any questions on percent excess, limiting reactions? So what should you be able to do? You should be able to calculate percent excess. You should be able to identify the limiting and excess reactants. You should be able to do some quantitative calculations. You should be able to take specifications in this language. So if I give you some of those numbers, you can turn them into equations that then you can use in reactor design. One of these, so one thing we can specify is excess and limiting reactions. Another related to this is called fractional conversion. Questions? Get conversion on? Okay. I think you've done fractional conversion in chapter 2 and 3 problems. Now we'll put some basically this language behind it. I need to know this chart. So fractional conversion. Can you guess what it means? It's just what it sounds like. It's the moles. It's what fraction of stuff actually gets converted to product. That's all it is. So in math, I'm going to take the moles of the reactant consumed. I'm going to divide by the moles of the reactant fed the reactor. Got a number? 0.52. Anybody want to disagree? Yes? How many agree? Cool. Okay, so what do? We took reactant consumed was 131.2, the stuff fed was 254.2 kg moles per hour, kg moles per hour, units canceled, it'll be 52% conversion. Okay, so let's do some math. Okay, so you get the idea? Again, I want to give you some language and some math. Moles of, let's start with the material balance. So, derivation. Typically we have amount of component that comes out equals the amount of a component that goes in plus the stuff that gets reacted. Nu IK times IK dot over all K reactions. Right? That's my typical balance for a steady state, continuous flow reactor. The stuff that comes out is the stuff that goes in plus what gets reacted. So N dot I in minus N dot I out equals opposite the sum over all K reactions nu IK times I dot. This is my moles of reactant consumed. Okay. So the moles of reactant that gets consumed is basically in minus out, or another way to say it is the sum over all reactions times the extent of reaction times the stoichiometric coefficient. So those are my equations for continuous flow. In a batch reactor, I don't have ins and outs. Instead, I've got initials and finals. So I'm going to rewrite this also in terms of initials and finals. Batch reactors, FC, fractional conversion of component I, is the amount of component I at the beginning, no dot, because it's just not so the stuff at the initial, the time 0, minus the amount of component I at time final, divided by the amount of component I at time 0. So how much is consumed is the initial minus final. And how much we fed is the same as saying how much we charged the reactor with initially. Again, we can put this in terms of all K reactions. Now we would have the integral from time 0 to time final. Nu IK I dot K dt divided by N I initial. Okay, so this comes out of, on the top, that comes out of my material balance for moles of things in a batch reactor. Sum over all of the reactions, how much moles is being consumed as a function of time through the time period. Okay, over the number of moles at the end is 1 minus fractional conversion of I times the number of moles fed. no dots over any of these, even xi dot. No, xi dot has a dot because that's a rate per time. Rate per time. Okay, any questions about fractional conversion definitions? Okay, so some of your homework has fractional conversion stuff, and you have to convert those into equations like this that then go in and give you a specification that helps you solve things. Okay, I want to do one example before we go. Back to our friend, the Haber process. N2 plus 3H2 goes to 2NH3, we make some ammonia. Let's say we're given 2 and H2 fed to a reactor at a 1:5 ratio. Which one's in excess? It's 1:5 ratio, which one's in excess? When I say hydrogen, when we say nitrogen, okay, it's hydrogen. We should have 1:3, we got 1:5, we got more than hydrogen. Let's see, let's say the nitrogen feed rate is 1,000 kg moles per hour. And let's say xi dot, the extent of reaction, is 1,000 kg moles per hour. So what's the fractional conversion of N2? That's the question. 100%. So has xi dot times nu N2 over N2 in is 1,000 over 1,000 equals 100% or 1. How about the fractional conversion of H2? Same formula, nu now is 3 times xi dot over NH2 dot, so I need 3,000 over 5,000 is 60%. Great. What if I change the problem and instead of telling you the feed rate, what if I tell you we need to produce 1,000, but I say, what if fractional conversion of N2 is 50%? So this is, we did stuff like this in chapter 2 and 3. We said everything converts and what comes out. What if I say only half of it converts? What's my N2 feed rate got to be? How much? 2,000. 2,000 kilogram moles per hour. I'm going to convert half of that. So then what's my H2 feed rate going to be? So let's see. I'm still going to react. Well, if I'm going to keep this 1:5 ratio, say I'm going to keep that. I need that spec. Then I'm going to have 10,000, right? What if fractional conversion is only 10%? Now I'm going to need 10,000 kg mole. I'm going to need 50,000 kg mole. What's the problem here? What should we do? Is there a problem? Is that okay?
Cost is real high.
Why? Okay, it's going to cost a lot more because
We're not like getting out as much as we can.
we're not getting out as much as we can. We're going to have to buy a whole bunch of hydrogen to purify it. We're going to need a lot of nitrogen. So cost. What else? We're almost done.
Time.
Time. We got excess stuff. Excess hydrogen at the end. The other thing is we've got a huge flow rate, all those pictures of reactors, we need a huge reactor to put 10,000 kilogram moles per hour through. So we need a much bigger reactor. That's going to be more cost and more hassle. How can we get around this? Catalyst? Yeah, Haber's already got the catalyst. Good idea. So catalyst will lower the free energy, right, of the transition state. So it'll make it go faster. But what determines the fractional conversion? If it goes, let's say it goes to equilibrium, what determines the fractional conversion? At equilibrium, it's all about the change of free energy. Remember this? So we can calculate at equilibrium. So if the equilibrium is not that different, right? Glucose, fructose, that example, that's always 50-50 because they're the same molecule. If it's not that different, you can't beat thermodynamics, so maybe you only get 10% conversion. So what can we do? We've got tons of stuff coming into this reactor, tons of stuff coming out, not even reacting. What do I do with it?
You can recycle it.
Let me separate out the good stuff, put it back in. That's what we'll talk about on Friday. One of your homework problems is a recycle problem. Start calculating that. All right, see you then.
In the winter